Hello, everyone. Welcome to ITS520. Today, we're going to continue our discussion from last week. And I think we left off at optimization. So, yeah. All right, so you've had now your second homework assignment. All right, and if you remember, I talked about how that was really two things: scraping the data off of those websites. And then once you've scraped the data, you need to convert it into the format that we would need, for instance, to be able to do machine learning in Weka, all right? So usually when I say that, I'm going to use the terminology, convert it to the vector space model, all right? So that will be, going forward, I'd like to get the terminology down so you guys always know what I mean. But so that's going to be converting to the vector space model. All right, so that's what we're going to do today. So today we're going to start sklearn, all right, which I kind of hinted at last week. I just have some slides, but now we're going to look at yet another tool, the sklearn set of libraries, which will be very useful, all right? And it's just one of many libraries out there for machine learning for what we are doing. So that's the plan for today. Finish up the slide. So I'm going to pick up with optimization. That's where I'm going to start today, kind of motivate that, kind of give you some important information about that. And then after that, we're going to just jump into sklearn. And I'm going to show you, one of many ways in which you can create the vector space model. Okay, so it's one of many. There's a lot. Hopefully by now, the vector space model is starting to make sense. It's certainly something that will take a while. I mean, I still, it's funny, but I still remember literally the day that I understood this, because I remember struggling with it for some time, kind of trying to figure it out, and I couldn't understand it. And then there was like a moment, like, aha, I get this, right? And so one of the biggest things that I want you to understand about in machine learning is understanding how to go from raw data, like what you're doing, scraping RSS, websites and whatever, and then going into something that looks like iris. And that whole process is basically establishing the samples, the features, the classes, and then I'm talking about for supervised learning here, and then coming up with the vector space model representation of your data, taking some problem that's really abstract, that could be just about anything, and making it a little bit more structured. Okay, so that's so that's something that that is a very key component. Okay, all right. So now, before I begin, as you can see, I have the topic there, optimization. Let's actually go over to the course syllabus or course Brightspace. So I've been playing around with this. Machine learning is a field that it used to change quickly, and now it changes at the speed of light. I mean, it's literally, you look at the libraries, sklearn, TensorFlow, Pandas, NumPy, all of them, they're just updating things constantly, right? And making things more efficient. Because as you know, Python is an interface over C. So everything is always being made faster, more efficient, to be able to handle more data. So everything is changing constantly. And actually, you guys are lucky, because this semester, I'm doing kind of an update of this class of 520. Not that it was outdated by any means. It was well within where it should be. But there just have been so many changes. And so you're lucky in that sense. And I've been thinking quite a bit about how to reorder the topics. So as you can see here, so far, I'm pretty happy with the flow that I've been following. You know, intro, WECA, performance metrics, data sets, and we're here at data scraping. So if you notice, I moved sklearn a little bit ahead. So I decided that it would be more useful to have these tools, and I've moved NumPy a little bit further down. So instead of giving you so much of the intense background, I just decided to move that a little further down. And so we're gonna do sklearn, and then you'll have your next assignment, which is Twitter, but it'll be very similar to the data scraping. So this is really just a homework, not so much a lecture. And then after that, we get into supervised learning. I'm still debating here. We could do these in sklearn. We could do these in NumPy. We could do these in TensorFlow, right? So I'm still debating which way I'm going to go with this. But all of the libraries are pretty much sometimes interchangeable. Like TensorFlow is literally just a rewrite of NumPy in some sense, in some ways. All right, and so you can see here, my goal is to cover all these things and to get the reinforcement learning as soon as I possibly can, so I can cover all three areas. But just, this is just kind of an outline of where I see things going with the class, okay? Just be aware, you know, it will change a little bit. Now, sklearn, I wanna stress, I don't view sklearn as a difficult thing to learn, which means don't spend, or rather, let me rephrase that. Spend a lot of time on it on your own, okay? Don't procrastinate. If I introduce this, start, you know, using it, make sure you understand, because sklearn is easy, okay? Compared to the other things we will do. And so I will move fairly fast through it. Now, it should be easy, and you'll notice it's easy. But I just want to stress, where sklearn is something we're going to use it throughout, but it's not like I'm going to spend a lot of time on it. Okay, so certainly pay attention today. You know, if you have any questions about it, please go ahead. You will see it's pretty straightforward. It's not GUI anymore like WECA, but sklearn is literally like WECA. All right, so whereas WECA is option A, or let me put it this way, WECA is a hammer. But it's a nice hammer with, you know, some like an interface. sklearn is another hammer, very powerful hammer, but it requires you to carry it a little bit more, right? So you have to do a little bit more of the wielding of it. It's going to be coding now, so not a GUI interface. So just be aware. So it's a light introduction to make the transition from GUI to to more Python scripting, to the more advanced libraries like NumPy and TensorFlow, okay, and Pandas. Today I'll introduce Pandas a little bit, but again, remember that the goal is not to introduce Pandas, so sort of learn that on your own as well, okay? Pandas, very powerful library, as you will see. I'll provide some examples of how we can use it. All right, unfortunately, that's one library that I cannot spend too much time on in this class. All right, so that's kind of the idea of just showing you this. We're currently on week 6. So 2 things about that. Number 1, we'll have an exam, I think sometime around fall break, right? That's coming up, I believe. So, so just be mindful of that. There's an exam coming. Also, given that we are currently on week 6, it wouldn't be a bad idea to start thinking about term projects. Okay, start forming form groups of 2 students, so groups of 2, no more, no less, and start thinking of something that you would like to do. Most of it will have to be a supervised learning kind of a problem, like what you're doing with data scraping data. I don't get to introduce reinforcement learning early enough for you to do a project in that, or in unsupervised, right? So these get covered towards the end of the semester. So I'll try to cover them relatively as soon as possible, but I feel that you know, if you remember, we divided machine learning into supervised learning, unsupervised learning, and reinforcement learning. Definitely your term project should be in supervised learning, okay? All right, are there any questions before I get started with the slides for today?
I just wanted to iterate that. So like the homework was not like there was nothing to turn in for it today, right? We were just supposed to try to run those programs and get that first part done.
I think I said that I was going to give you 2 weeks for this homework assignment.
Correct.
Okay. So it's not due today. It's due a week from today because I still need to give you the second part of it, which is, you know, we'll talk about it, and you know, I want to see where you are with it, but then I need to give you the second part of it.
Mm-hmm.
Okay.
Yep.
Other questions?
Mm-mm.
No questions? The videos are now posted, so I had forgotten to do that, but that I just did that just before the class, so the videos are posted. Also, if you just subscribe to the channel, you can get them that way as well, because I definitely always load them to the channel, but I sometimes forget to do the link to the website. I will do the link as well, but you know, the channel does get them right away because that's something I have to do. Yeah, for the term project, I had a question about how do you form your groups? Form groups of 2, just pick a person, you know, that you want to work with. If you can't find a person, maybe in the chat, you can, you know, just say, I'm looking for someone, and then form your group. Again, as I said, you know, it's early right now, but start thinking of what, you know, kinds of things you would like to do, maybe something that you've heard about, and then I can give you some information as to whether that's something doable for 520 or not, okay? But yeah, please start thinking about the project and forming your groups. Any other questions?
Would be helpful if you give us a topic.
Give you a topic. I mean, it's machine learning, right? So you can literally do whatever. So I'm not going to be giving you topics, but one thing I am giving you is that it's a supervised learning problem, right? So if you understand supervised learning, you understand, okay, I'm going to be doing a classification. I need to find, you know, 1, 2, 3 classes. You need to define all of those parameters.
Oh, okay, I got it. The
whole point of the project is it's not a homework, right? When in a homework assignment, I give you a very structured thing. Here, I want the opposite for the project. I want you to pick a question or an idea. So for instance, I'm not saying do this, but you know, who's going to win the election, right? You know, this year. Okay, so how you know, somebody, you want to become a consultant of political, whatever that's called, marketing. So who's going to, or political analysis, right? So you want to start a firm with that. What would you do? Well, you know, probably get data from social media, right? Scrape Twitter, RSS feeds, Facebook. But you need to then craft the problem in such a way that you can build some kind of classifier. Now, it doesn't have to be a classifier that solves every problem in the world. You just define what you want to do, and then you define the pipeline, show evidence that you got some results. Does that make sense? So I'm not so much looking for an exceptional solution. I'm just looking for your thought process in being able to take an abstract problem and frame it as a machine learning problem, where you obviously get results of some kind. Any other questions? All right, it seems like there's no questions. Hopefully I'll have your first homework assignment graded by today. So I'm shooting for that. If not, I'm doing exams tomorrow. So while students are taking their exams, I will catch up on grading. think you've only submitted one assignment anyway. All right, so please, if there's any questions, interrupt me at any time. This is a very important, you should be seeing, first of all, my slides, right? And the slides should say optimization, okay? So hopefully that's what you're seeing. So this is a very important word in machine learning. It's literally the most important word in machine learning, because ultimately what machine learning is this, right? So, you know, optimization is something it's been done for many years, you know, in engineering and in business and everything, right? You know, it just means finding the best results, right? So traditionally, you know, this comes from applied mathematics, right? You know, it's used in, you know, statistics for, you know, say to solve linear, linear regression, right? It's just a procedure that you follow. You know, in operations research, in industrial engineering, in all kinds of areas, optimization exists in one way or another. As it turns out, in machine learning, you know, that's what machine learning algorithms do. They perform optimizations. They look at a problem. They frame the problem as a set of equations, and they need to optimize those equations to be able to produce good results, right? So I get this question, people always ask about optimization, and, you know, you could literally take years of courses in optimizations. There's so many techniques out there, you know, that I'm sure you've heard about. In machine learning, we don't use all the techniques. In fact, we only use, it's funny, but there's only really one of all of those techniques that is used for the optimization process. So we will talk a little bit about that. And the thoughts actually of people with regard to that. All right, so before I get into it, I should say a couple of things about optimization. First of all, you should know what optimization is. You should understand that that's going on in the background. However, nothing that we will do in the class will require you to explicitly write code for optimizations, right? So all the optimization procedures, you can think of them as already being done behind the scenes for you in all the libraries. So Weka had optimization, but you didn't really have to worry about it. It's done for you. sklearn, TensorFlow, PyTorch, you know, all the machine learning, you know, CUDA, all the machine learning libraries out there will all in some way do this for you. So it's almost like a thing where you have to only understand it theoretically, you know, and understand the background of it and the implications of it, but you don't actually have to, sorry, that's my phone upstairs. So you don't have to, you know, do the optimization yourself. You can all basically rely on this by the library. So the libraries do it for you. However, I do think it's really important for several reasons. First of all, to gain an understanding. So this is where another area of mathematics comes in, which is calculus. All right, so calculus comes in here. However, you should understand the intuition behind it, but, you know, you don't necessarily have to do any calculus here or have taken a calculus course. However, if you were, let's say, building your own library in CUDA, TensorFlow, PyTorch, right? You're actually building your own functions. Okay, then you would need to know this calculus and write the code for that. However, that is not recommended, because you will never acquire, even if you did everything correctly mathematically, it's unlikely that your programming skills are going to be as good as the programming skills of a team of 200 people at Google who optimize, and I'm using now, well, let me use another word, who perfect the way they write the code so that it's fast. All right, so your code might be theoretically correct, but guaranteed it's going to be much slower than anything that they can do. So in real terms, when you're trying to translate, build a corpus of the tech, doing translation of millions of things, Google's library or Facebook's libraries, PyTorch, when they take, a day, yours will take 2 weeks, right? So it's just not efficient. Now, if you really want to pursue it, certainly go ahead. I mean, it's in particular for research, right? For research. If you just in the future become a practitioner, let's say of cybersecurity, but you use machine learning, or you, who knows, you actually go in and become an AI, practitioner in a company, okay, you will still use just the tools. You will not really get into the meat and bones of optimization, okay? However, if you become a researcher, maybe, do your Ph.D. or something like that, or go work for TensorFlow in the group that develops TensorFlow itself, right? Then you would be doing this, and just be aware, you wouldn't be writing in Python either. You'd be writing in C, C++, all right? So a lot of this has to be done at a very low level so that it's efficient. Okay, so I do want to stress that you don't actually have to code these functions. Even if you did work at a lower level, like the CUDA libraries that NVIDIA provides for their GPU processors, you still would use CUDA's libraries, which already do a lot of this for you, okay? So I do want to stress that. However, it's important and eye-opening to understand how all of this works. All right, so are there any questions before I continue? Okay, so before we begin to discuss some of the machine learning algorithms, I should say, as I said, something about optimization. It's always a good idea to have that intuition. Optimization is a key process in machine learning. Basically, any supervised learning algorithm needs to learn a prediction equation, all right? So there's gonna be some kind of an equation given a set of annotated data. So what that means is that, let's say you have an equation like this. This is times dot, 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 is a bias, right? So this is, let's say this is the equation you're learning in machine learning. And these are the labels. And the data, like in Iris, that F1, F2, F3 are these X1 and X2. But then you have these things, the W1, the W2, and the bias, right? Which are called the parameters. And the parameters are the thing that, and you can see that written here, the parameters are the thing that you need to learn. Okay, that's what the model learns. So as you can imagine, one simple way of thinking about this is if you had a quantum computer that can perform, a good, a trillion calculations in a nanosecond, you could probably just try random parameters, this, set a random, see the results, because whenever you do that, the model basically, you pick a set of parameters, you give it X, you give it Y, and then you measure the results, right? How does it predict? Does it predict well or badly? If it doesn't work, try another set of parameters. If that doesn't work, try another set of parameters, and so on. So if you could just do that, in an infinite amount, in a nanosecond, you could probably just try all the combinations in the universe and then find the thing that's the best. Obviously, we don't have computers like that. And so instead, we need to, we're going to need to be more efficient. So there's going to be some kind of an optimization algorithm that we need to use in particular. Okay, but basically, as this states, any supervised learning algorithm needs to learn a prediction equation given a set of annotated data. This prediction function usually has a set of parameters that must be learned, which is what I just said. However, the question is, how do you learn these parameters, right? So what is the technique, the algorithm, the methodology? And the answer is that we do so through optimization. So that is to say, we don't just pick the parameters randomly and try all the parameters in the universe. I mean, sometimes you have millions of parameters. It would be impossible. You would run out of time in the history of the existence of the universe to try all calculations, unless you had some kind of a computer that doesn't exist today. So instead of doing that, we can't do it randomly, so we have to try optimization. In its simplest form, optimization consists of trying a set of parameters with your model, like I showed in the previous slide, and seeing what result they give you. Okay, so you get a result, you know, is this a cat or a dog? Well, the model says cat with these parameters. We look at the real image given the data. Oh, that was a dog actually. So that's incorrect. Okay, try another set of parameters. Try it again. Is this cat or a dog? Cat. What does our image look like? Cat. Okay, this set of parameters seems to have somehow done better. And so now the question is, how do we know that we should use these parameters and not the other parameters? Usually these parameters are called weights. And you can see that I actually wrote W's here. And that just means the weights, basically. A weight is, you know, intuitively, you probably understand this as, you know, you're going to get $1,000 a week, but based on performance. So that W is a performance metric. So your boss is going to say, no, you were not very effective this week. I'm going to give you a 0.70. Okay, so now how much did you earn? You didn't make the 1,000, right? You made 700. Then in another day, you were very efficient and your boss says, okay, 1.0, that day you got 1,000. So that's what is happening here. You're just, the weights give more strength or less strength to the data itself, okay? So if the result is not good, you know, the optimization algorithm, and notice that now this is being introduced. So it's not just about optimization, there's a ton of optimization techniques. So you have to, and sometimes the optimization technique depends on the type of approach that you're taking, okay? So keep that in mind as well. So if the result is not good, the optimization algorithm needs to decide if you should decrease the values of the parameters or increase the values of the parameters. So that's the idea that, you know, we had x1 plus x2 and so on. So now the weights, I'm just going to write them over here, W1, W2, could be different parameters. I mean, believe it or not, this is all we're doing, right? So we're saying, you know, notice this idea. If the result is not good, the optimization needs to decide if it should decrease the values of the parameters or increase them. So that is to say, well, here I said this was a 0.8 and this was a 0.1, but that was not good. So now I'm going to increase them. So this is 0.9, but this one I'm going to decrease to 0.01, right? So that's what you're doing in optimization, and you can see the values can increase, decrease, and you have that little game going on. So for this, we're going to need an algorithm. But like I said, it is an algorithm that is built into the machine learning algorithms themselves. Okay. In general, you do this in a loop. All right, you do this in a loop where you're increasing and decreasing until you find an optimal set of parameters. And that's what an optimization is. That's why we do this idea of training, right? Training just means we give it the data over and over and over and over again, and eventually the model starts to do well, okay? So the model starts to do really well, but you have to find some way of measuring that, okay? So you have to find some way of measuring that. In a very true sense, machine learning is really that. You know, you're constantly just giving it giving it data, and it's learning. However, these algorithms are not, they're a lot of people say that these are not the algorithms our own brain uses, because our brain does not, as I said, said before, does not need 100,000 examples of you falling or of you tripping on a cable to stop tripping on a cable, right? So it takes one. You trip once, you learn, right? And so so we probably, our mechanism of learning in our brains is probably a little bit different, more advanced in some way than this. But for machine learning, this is all we have. So I'll talk a little bit about that as well. How in a very true sense, everything in machine learning is built on this one thing. That's why I definitely needed to cover optimization, because it is like the one piece in the link that influences everything, okay? So one of the questions to answer here is, do the values go up or down, right? So, I keep saying we increase them, this one goes up, this one goes down, but how do we know, right? So like I said, in a very true sense, if we had a computer in quantum computer in the future, maybe we could try all numbers at random really fast. That's not possible today. So instead, what we need to do is what is called a search. We need to search the parameters, and we need to look at them and try to figure out what's the best set. Is this better? So is this better than this one? Which combination of parameters is the best? As it turns out, there are methodologies based on calculus that help to make this decision, okay? So that's, again, calculus comes in to help us out to determine how this works. So here's the best example of understanding this, an optimization graph, okay? So in a very true sense, this is what's happening in a machine learning algorithm, okay? You use an algorithm here called gradient descent. Okay, gradient descent is the algorithm in question. So what is the idea here? The idea is that this curve that you see here represents the underlying machine learning algorithm that we are trying to build, okay? So we are trying to build a machine learning algorithm, and all it is, as we've talked about it before, there are two graphs, right? One graph of the data itself, where you're trying to plot the function that divides the data, and then there's another graph called the optimization graph. So there's two of them. So in one graph, we have the data, right? And we've talked about this already. So my machine learning algorithm is really that, a line, right? That line is the best classification line, okay? Because it minimizes the number of errors. If I do this line, it is worse because I have more errors. So what happens here is that this function, or this line, is a function, right? We've already established that mx plus b is the function of a line. It's something that we learned in high school. So now, that function also, in a very true sense, determines the shape in the other graph of this function, okay? This function. So there are very nice machine learning algorithms, like something called support vector machines, SVM, which by the nature of how it is, we're not going to get obviously into the details of it, but just by the nature of how it is, which, if you remember, it's the one that has the margins on the sides, right? Because of the nature of what it is, its resulting optimization graph looks like this, what is called a quadratic function, okay? A quadratic function is a function that looks basically like that, like a bowl. You see that? A bowl is very nice because think of it, like, if for those of you that like skateboarding, right? You would go to those pools that have like a round shape, right? And you can go skateboarding there. There's Johnny skateboard, right? And so you're basically just doing that, right? You're moving like that. So you're descending, you're going up and down this gradient in the pool itself. That's a very nice thing because of gravity, what's going to happen eventually? Once you lose momentum, you basically end up at the bottom of it in a fixed point, okay? However, other optimization techniques, let's say that we have this problem, right? So this cannot be separated with a line. It has to be separated with more of a curved type of a function. So this would be an example of neural networks. Neural networks will have a shape in the data space like that. But in the optimization space, which is another graph, the shape will not look like this one, unfortunately. It'll look more like this. You see that? A little bit more complex. This is intuitive, just meant to be intuitive, but it's a function that's a little bit more complex. So if you're the same idea, if you're a skateboarder, it's not going to be that easy as it was before, right? Where you just let gravity take you to the bottom. Here, what's the problem? Well, the problem is it very much has to do where you start. So if now you're the skateboarder and you want to get to the bottom of this, well, obviously the bottom is that one, right? That would be the bottom. But if you're a skateboarder and you start here and you let gravity take over, what happens? You end up there. Do you see that? If you start here as a skateboarder, gravity will take you and you end up there. So the problem is, depending on where you start, that's going to determine where you end up. So in a very true sense, some algorithms like SVM, that have quadratic functions ensure a function that looks like this, like a bowl shape. There's only that. Doesn't matter where you start, you're almost guaranteed to end up at the bottom. But in other algorithms like neural networks, it doesn't work that way, right? It very much where you begin is where you're gonna end up likely. So you end up there, right? So these functions have an optimal minimum, whereas these functions have an optimal minimum, or called a global minimum. And they have local minimums. And the problem with these algorithms is that sometimes you can get stuck in a local minimum. So what does that mean? It means that you solved the problem because, obviously you didn't end up here, right? You ended up here, so you achieved some performance, but your algorithm did not give you the optimal. So in a very true sense, if you were building a classifier to make predictions about the stock market that could, make money for you, with this one, you might get $500,000 a year. With this algorithm, if you end up here, you get 100,000 a year. But if you had found this point, your algorithm would have been so good that you could have made 4 million a year. Does that make sense, guys? Does that intuition make sense? Guys? All right, good. So again, remember please that there are two graphs. There's the graph of the data itself. The graph of the data itself, that one. And then there's the equivalent graph of the optimization problem. Okay, the optimization problem. So now let's analyze how this works. So the class, now neural network, in the previous example I just showed, also why neural networks and deep learning in particular can be better than SVM. So SVM used to be back in 2011, 2012, used to be the winning algorithm. Everybody was obsessed with that one. Now, because it was a beautiful thing mathematically. It was, mathematically beautiful, like it looked like this. But the problem is, as I said, SVM gives you 500,000. Then come some people that do deep learning. Deep learning, the function of deep learning looks, as I said, like this, crazy. But they figured out methods that allow them to find that optimum. It's more complex to search, but it works, and it translates into 4 million. So immediately every company drops this and goes for that. And it's just, it's just economics, really. All right, so anyway, so now that we sort of understand that idea and motivated why deep learning is better, let's just think of how we do this search, right? So this search. So this search is very much, so I use the term gravity, like a skateboarder, just letting gravity, let it get to the bottom. It's not gravity. Instead, it's more of a search where you can do, so you have a little bit more control. So usually what I like to say, it's like you're a giant and you're walking here. So you're walking, right? You're walking on here and you're making decisions. So for instance, you can say, I'm gonna walk down, or you know what? I'm gonna walk back up. That's basically the algorithm. The algorithm looks at this function, and every step in that loop that it was mentioned, in that loop, you're somewhere. You have to start somewhere. So let's say you're here. Imagine you're here. Right? You're there. If you decide to go in that direction, what's gonna happen is you won't get to the global minimum. But if you continue in this direction and actually go up this, then you will eventually find the optimal minimum. Remember that that you're at an optimal because it's a supervised learning problem where you're trying to determine some cost, some penalty, right? So remember, it's always about minimizing the sum of errors, right? Minimizing the sum of errors. So again, that translates to remember, this graph is related to this graph, completely related. So for instance, if I pick that one, I have a lot of errors because these are going to be marked as X when there's zeros, and these will be correctly marked as zeros. So that means that error is going to go up. So in relation, that's like saying you're here in gradient descent. You're there. So that's not good. But then you kind of figure out where you are, and you end up here, right? You end up there, and now that translates into a line that looks like that. Okay, it's always about picking the set of parameters that defines that function, and then you measure if that function does well or not in the real data. So that's why this graph has cost versus parameter. So what that means is the W, let's say W1, W2. So this is W2 for this line, but this is W1 for that line. You see that? So cost is the other axis, which determines the number of errors. So this one had fewer errors. This one had more errors. So here, for instance, if I wanted to plot this, I would say this is probably W2. You can see in relation to cost is high because the cost just means the number of errors. This translated into this line, which gave me a lot of errors. Now I do W1, which is this line here, and this one associated with this has a lower cost, which means it's this line, and if you look, this line will correctly classify both groups, X and Y, and so it is a better one, okay? And so the data graph in the optimization graph shows you how to pick the weights or the parameters. So obviously you would conclude this parameter is bad because it's got a higher cost. This one is better. So then just get rid of that line. You don't want to do that one. And instead you want to go with W1, which gives you that line, which minimizes the number of errors. Does this make sense, guys? All right, are there any questions? Feel free to ask questions. I mean, these are important concepts. All right, so it doesn't seem like there's any questions. So now then, the question you might have in your mind is, okay, that's all great and all. I understand that sometimes they have their perfect curves like that. Sometimes the curves, you know, look like this. And very much you need to start at multiple positions, right? So that you increase the chance of eventually finding the optimal. This is more like SVM, a machine learning algorithm. This is more like neural networks or deep neural networks. Okay, so in both cases, it's the same, right? In both cases, you have a giant walking over here, or you have a giant walking over here. So in both cases, it's the giant going over here. But remember that the giant can choose to go in either direction. However, the goal of the giant is for this cost to be the minimum. All right, so the giant wants to minimize that cost. You know, it's like saying, you know, that's where I'm going to pay less, or where I'm going to find the treasure, or something like that. Because these W's determine the shape of the function that divides the data. You know, that, and so on. But the question now is, how do I know at each iteration whether I should go up or down? That's really the last piece of the puzzle. And that part is, so you want to reach basically the star, right? That's the optimal. You're not going to get, so basically that's the limit of your algorithm. Obviously your algorithm still has some cost, right? You didn't quite get to zero because it's just not possible with, you know, what you have. Maybe someday a new algorithm will be discovered, which, you know, does something like that, and then the cost is reduced even further. But for now, the best algorithm can only give you that. So the question is, how do you decide as the giant whether to go up or down? And also, there's another piece. The step that you take, there could be a giant that's that big versus a giant that is not a giant. Maybe it's a smaller person. So the step size of this is bigger than the step size of this. What that means is that the algorithm can advance faster in the function, okay? And that is both good and bad. That is both good and bad, because you have, imagine you have this, right? If you had imagine you have a very tiny person there. So it takes a step, then a step, then a step, you know, that's a lot of little steps. If this is really huge, your algorithm will take a week to process. But you're guaranteed that eventually you'll find the optimal. On the other end, you could take a giant that is extremely big, right? Well, this giant takes steps that are like this. So what's the problem? The giant will jump from here to there, to there, to there, to there, to there, never reaching the optimal, okay? Never reaching the optimal. And so what that means is that you want to have the step size that you decide, which is the size of the giant. You don't want it to be too big or too small, okay? So just intuitively remember that there's going to be a parameter in all machine learning algorithms called the step size. And that's just the size of the giant. So usually you have some numbers that say use a value like 001. That just means that's the giant that is about right. However, sometimes you can also do little tricks. Like, you know what, I'm going to start with a giant like this one, but as I train, I'm gonna reduce the size of the giant to that. So that is called a variable step size, and that's also possible. But anyway, we will see a little bit more of that later on. But hopefully, I think intuitively this should make sense. I mean, the analogy is very true, and it's very real for us, right? All right. So now the question is, how do I know if I'm here to go in that direction or that direction? Or if I'm here, how do I know? And what if I'm here? Do I move? So intuitively, obviously, we look at this and we know, well, I want to go in that direction here because the star is down there. If I'm here, I want to go in that direction. And if I'm at the star, I don't want to go in either direction. I just want to stay where I am. That basically means I found my optimum. So how is that accomplished? Okay. And so the algorithm of gradient descent, that's where it comes in. Oops. Gradient descent is the algorithm that actually has defined this, and it uses calculus to solve it. So the above graph represents an optimization problem. The y-axis represents the cost or penalty of using a given parameter. Now notice that I'm only showing this here for one parameter, w, right? But this would be done multiple times for all the parameters. It has to be done efficiently and taken into consideration for all. Here, I just want you to understand the intuition, so I'm just really going over this, for one example. So the y-axis represents the cost or penalty of using a given parameter. The x-axis, on the other hand, represents the value of the parameter w being used at the given iteration. So remember, I gave you the example that I could pick w1 there or w2, which is a different w, but notice the relationship with the cost function is really what matters, okay? That's really what matters intuitively, because our goal is for this cost to be as low as possible, which is the cost of the errors, all right? The cost of the errors. So the curve that I showed you before represents the behavior of the function being used to minimize the cost. Oh, sorry. There's a typo there. The curve represents the behavior that the function being used to minimize it will follow for every value of parameter w. Exactly, yeah. So there are actually, in machine learning, two functions that you learn. There's the mx plus b, which, as you know, that's just a line. And then there's the cost function. I'm just going to use the standard least squared errors function. There are many, which means I have my real sample, and my predicted sample. I take the difference of them, square them, and that gives me the difference. And then I just take the sum of all of these in my data set, and that is represented, if you notice, that is represented as the quadratic function over here, right? Where this is cost, because we're calculating a cost given parameter w. Because the parameters come in this one, right? If this is the predicted, it's actually, whereas this is the real, this is w x plus b. So what that means is that this w that I pick here determines this function, which determines the predicted value, which in turn, the predicted value gets compared to the real. So this is the real, and this is the pred. Does that make sense, guys? Took out the square. Make sense? Questions? All right. Feel free to ask any questions. This is a very important concept. We will look at this again for those of you that take the deep learning class, because in the deep learning class, I go into more detail about this. But here, It's just meant to be an introduction to these ideas. All right, so the curve represents then the behavior that the function being used to minimize cost will follow exactly. So if I pick that W, the behavior results in that. If I pick this W here, the behavior results in that. So that's what, and that translates into this one over here. So we're talking about gradient descent then, that's the algorithm, all right, because we want to figure out which way to go in the curve, right? Which way to go. So we're the giant again. And so do I go in that direction or that? I want to go in that direction, but I need to make a choice. So I basically need to figure out where am I in the function itself. All right, so as shown in the graph, the optimal value for the curve is found where the star is located, where the value of cost is at a minimum. So somehow the optimization algorithm, gradient descent, needs to travel through the function and arrive at the position indicated by the star. So the giant, right, needs to travel somehow. At that point, the value of W reduces the cost and finds the best solution. So again, you know, that means that W was not that one. That's a bad W. Instead, we have a W that's a little bit more like that, right? So this is W2, W1. Oops. W1, which is the set of parameters. So that's what that means. At that point, W, the value of W, reduces the cost and finds the best solution. Now, instead of trying all the values of W at random, which, as I said, it's not possible, the algorithm can make educated guesses about which direction to follow, up or down. So that's really all that we need to figure out is, do I continue to go up or do I continue to go down, you know, to help myself? So instead of, you could randomly just go up and then see what happens, then randomly go down, but that's going to take forever, right? So you can't do that. You want to make educated guesses. So to do this, we can use calculus to calculate the derivative. So the derivative, if you've never taken a calculus class, the derivative is just, you know, a way of taking a function, apply a mathematical operation, and it gives us another representation of that same function. Okay, so don't worry about that so much, but it's like a transformation of the function to another function, and of course that has meaning, right? And that's really what's going to matter here, is that that operation of the derivative in calculus has actual meaning in what we're doing, and so that should give you some intuition of what's going on. So, excuse me. So what you do is, to do this, we can use calculus to calculate the derivative of the function at a given point. This will allow us to determine what is called the slope at that point, right? So when we talk about slope, notice how the algorithm is called gradient descent, right? And now we're talking about slope. And I keep talking about giants and like ridges and mountains, right? So you start to see that there's a pattern, right? So basically, you know, it's like that or like that. But basically now we can figure out what is called a tangent function to the curve. And that's what I had in the drawing over here. So if you look at this now, it might make a little bit more sense that what I did is, at this point, given this W and this function, I calculated the derivative of the function at that point. And what that gives me is, it gives me the slope, this line here, which is a straight line, which is tangent to the function, to the curve. And what that does is it actually gives me something very valuable. It tells me the shape of the curve at that point. So if the curve looks like this, I know that I need to go in that direction. If the curve, excuse me, if the curve looks like this, I know that I need to go in that direction. And if the curve looks like that, I know that it's parallel to the x-axis, because this is y and this is x. And so basically, I know that that's a stopping criteria, okay? So intuitively, that's what the derivative does. All it does is it kind of gives you a positive, minus, or a 0, right? You can think of it that way. It's kind of like, oh, it's positive, so go in that direction. Oh, it's negative, go in that direction. Oh, it's 0, don't go in any direction, you're done. Do you see that? So intuitively, that's what calculus is doing here, and it's actually a very useful thing for the algorithm. So that because it allows us to calculate or determine the slope at that point. Questions? All right, no questions, it seems. So again, all I'm doing, as I said, you won't have to calculate these derivatives. That's done by the gradient descent algorithm. But I do want you to understand the intuition behind it. So in the case of the graph, the derivative will represent the tangent line to the curve. If we calculate that derivative at point W, given that point. So it's always in terms of a specific position. So if we calculate the slope at that position of this, at the position of the star symbol, then the slope is 0. Because the tangent at that point is parallel to the x-axis. Right? So that, oops, it's a terrible line. Okay. That's what that means here. The slope at point W could be positive also. Based on this result, we can tell the direction we want to take for parameter W. That is to say, we want to increase or decrease. So it literally is that simple. Calculate the slope. If we're at this point, the slope looks like this. Okay, I know which direction to go. If I'm on the other end, I know which direction to go. This also applies if the function looks a little bit more like this, right? Because it's still the same. If I'm here, the slope could be like that. If I'm there, the slope will be like that. If I've arrived here, unfortunately, I'm going to stop my search. And so what you would need to do is you need to start your search at multiple places in this mountain range and keep track of the final cost. Hopefully you'll get to that one in one of your iterations. Okay? So that's why you repeat things sometimes, because even though you might be giving things the same data, since you're starting the parameters randomly, you're starting at different positions. And so one of those could give you better results. Excuse me. Right? If you get something like that, right? It's going to tell you the information that you need about the tangent and the direction that you should follow in it. So based on this result, we can tell the direction, a plus or minus. So now that operation gives us that. And this type of optimization is called the gradient descent algorithm, and is very important in machine learning and deep learning. In fact, it is basically, imagine if all of this is machine learning and deep learning. All of that is machine learning, deep learning. Gradient descent is the pillar that holds everything. Imagine that. This is gradient descent right there. The entire machine learning, deep learning depends on it. And it's really just one algorithm. I mean, there's multiple versions of the same idea. So there's like the standard gradient descent algorithm. There's also one called the atom optimizer, which is like an improved version of gradient descent. But ultimately, and I want to stress this, it's not like there are 10 algorithms for doing this. Everything is built on top of that, on top of this. So people like Jeffrey Hinton, for for instance, Hinton, who is the grandfather of deep learning, are really concerned about that fact, right? That they have built this amazing thing, machine learning, deep learning, but it's all built just on that one idea. So there's been a lot of creativity here, but for whatever reason, we're kind of stuck there, right? It's not like there's, you know, another one. Based on this analogy, maybe someone someday will invent a sturdier column, not gradient descent. And then who knows what will happen, you know, if that will revolutionize machine learning, deep learning, or if it'll just make it better, who knows? But for now, everything is limited to standing on the back of gradient descent. All right, and that's a very, very important conclusion there. You know, it's, you know, are we limiting ourselves, for instance, by just using gradient descent? You know, could we be exploring other things that will generate even more amazing things? Now, if our brain, you know, for instance, the human brain probably does not use gradient descent, because gradient descent requires, as I said, too many examples of something. You need to trip 100,000 times on a cable, right, for gradient descent to learn. Humans don't actually do that. So they you know, humans can learn in one step. So then it's possible that gradient descent is not the mechanism in the brain, or at least there might be some elements of it, but that just I don't know, you know, you can draw your own conclusions, but you might argue if we don't use gradient descent, then, you know, this is not how our brains work, right? So we're not going to achieve the type of AI that's human-like by these ideas. Or it could turn out that maybe you can. Maybe evolution took a direction and we take another direction with gradient descent. Who knows, right? But the whole point is, that's more philosophical there, but the whole point is that machine learning, deep learning is built on this one idea of gradient descent. All right? Anyway, so certainly a lot of researchers are looking into getting rid of that and coming up with other ideas and to see where that takes them. All right, so there are several approaches to implement gradient descent, and this is just the simplest explanation for conceptual purposes only, right? So I'm gonna give you a little bit of intuition of how gradient descent works. The basic idea is that you have a step size, right? And then you have the values of your parameters, okay? And then you have, so really you're trying to update a parameter. Let's say you're trying to update a parameter W, which I'm calling X here, but should probably call it W. So what do? You know the function, right? So you know the function of the line, right? So you know that. So it translates to a line, right? So you know that function. And then that function, you calculate the derivative of it, right? So you have the first derivative of it here, all right, of some number. As I said, remember, the derivative is just given a function, you get another function. There's a specific set of rules of how it works. It's very mechanical mathematics. Once you have the derivative, then this is the gradient descent algorithm. As you can see, it's very simple, right? All you have is, you have the parameter W in question, right? Let's say this is the parameter W. And now you have a step size, which is 0.01. And that just means the step size, remember, it's the size of the giant. So is it a giant like that? Or is it a tiny giant? A hobbit of some kind, right? So you decide that by the value that you plug in here. And then after that, you have times, and now you're going to calculate the new W. Basically, you're updating the W, right? So you have the old W, the new W, minus 0.01, which is the step size, plus this parameter here, the derivative of the function. And what that's going to give you, it's going to give you either a plus or a minus or a 0. If you notice, if you get a 0, all of this would cancel out and you don't update the weight. If you get a negative here, then negative makes this negative, and so it becomes plus, so W gets updated, plus 0.01 maybe. You take a step in the positive direction. If this one is it's positive, then this positive times negative is negative, so now your W gets updated in the opposite direction, right? And it decreases in size, okay? That's basically it. So as you can see, it's a very simple function where you take the old one minus some step size 0.01 multiplied by the derivative, which is just indicating whether it's going to be positive, negative, or 0. And you indicate with that the direction. Am I going to increment the value? Am I going to decrease the value, etc.? Here's an example of the derivative before, so you can see the code that I wrote here, 3x to the 2, right? So this 3x to the 2 minus 6x, right? All right, and you can see that. So this one, 3x to the 2 minus 6x is this one, right? And then you can see here, this is the function, the original function, right, of the curve, like, like that, or, like that. This is the derivative of it, the first derivative of it, and that's it. So you don't have to know this or understand this even, but just be aware. We take the original function, calculate the derivative of it, and then in there we do the processing, and that's going to determine this idea that at this given point we have the slope. And so that's going to return either positive or negative so that we can update this value with either positive or negative or 0. And that way we know how to increment or decrease the size of the function. So we can see that here in the previous code example, we assume a function of, x to the 3 minus 3x2 plus x. Remember, these again determine some type of a polynomial. That this function determines some type of a polynomial function that you have in there. It looks like that. It's some kind of a shape, like a mountain range. That needs to be optimized for parameter x, the one that we're trying to update, and we will need the value of the first derivative for each point x, or the derivative. And so the derivative of x is going to be f, f of x, and which is going to be that 3x2 minus 6x. How you do it, you don't need to know that. There's just a rule that says, given this function, I get the derivative is this. So there's a bunch of rules, but I'm not going to get into that. All right, and then it's pretty standard. Then after that, you calculate the slope. So the parameter x can be calculated in a loop using the derivative function, which will determine the direction to follow when increasing or decreasing the parameter x. So that function, as I said, returns that, which allows you to increase or decrease the step size. And that's it. That is gradient descent. Okay, and that concludes kind of an intuitive explanation of how optimization is very important to machine learning, how we do this search efficiently instead of trying to randomly decide if we're going to go up or down a specific point, right? Instead, we use gradient descent. I also talked about the fact that all of deep learning and machine learning, basically these algorithms are built on top of gradient descent. And there are some people out there like Jeffrey Hinton, et cetera, who kind of marvel at the idea, right, that Google's business model, Facebook, they're all lying, based on that idea of gradient descent. That's why those companies are always afraid that one day someone will invent something new and it'll just revolutionize everything. So they need to stay at the cutting edge of research because of that. But anyway, hopefully this concludes our discussion of gradient descent and optimization. That's pretty much all I'm going to say about it. My goal was to give you an intuition. You will never have to write this code at all, because this is the code that, first of all, your code would be very slow, most likely. And all of this is highly optimized in the machine learning libraries. Okay? Questions? Are you guys still there?
Yeah, I don't think we fell asleep on you yet. At least I haven't.
Well, all right. So no questions about this? Nothing? All right. So it seems like there's no questions. Okay. So now the next thing that we're going to do, I'm done with this part, the theoretical part. And now I'm going to switch over to the other set of slides, which are the sklearn slides. So now it's sort of, we're going to probably stop in a second, take a 10-minute break, and then that way we can start with the lab part of this week, which is sklearn. Okay, sklearn, as I said, is you probably, can you see it now? Are you seeing my sklearn slides? So you should be seeing a set of slides right now that says sklearn. All right. All right, so that's where we're going to stop. So given that I don't want to have these, it makes sense to keep these two videos broken up. I'm going to, it's 3:19, so I'm going to stop now, generate the video, and then we're going to start again at 3:29 with the second half of today's discussion, the lab, which will be about the sklearn Python library. Okay, so let's do that. So I'm going to sign off for 10 minutes, and I'll be back at 3:29.